All right, Chapter 9, Section 5, the sine and cosine ratios. Section 4 introduced the first of the three trigonometric ratios, being the tangent. And I took the time to make sure that we still had this marginal diagram over here, where, again, this is what we covered in Section 4, the fact that the tangent of some angle gives me this ratio based on that angle. And this ratio, whichever it's going to be for any of the three trig ratios, these represent positions, I should say rather, side lengths in a triangle, two of the three. Okay, so just to remind you about the definition from Section 4, what is a trig ratio? What does it do? Okay, a trig ratio, basically, whether you're taking the sine, cosine, or tangent, is basically relating some degree measurement, namely of the two angles that are not the right angle. These are what we would call the two acute angles in a right triangle. But it's going to relate whatever degree measurement is in one of those two angles to two other sides in the triangle, which seems kind of counterintuitive when you actually think about it, because degree measurements represent basically how far apart this wedge spreads. And so, like, the bigger the spread, the bigger the angle, the smaller, or the closer it is, the more narrow, the smaller the angle. Okay, but it relates that that degree measurement to side length, which is a different measurement entirely. Okay, it's a distance. Okay, and so there's this relationship that's created. And again, I spoke about it in the Section 4 notes in regard to the fact that we're dealing with similarity, actually. Where did these trig ratios come from? When you hit sine of some degree measurement in your calculator and it spits out this ungodly decimal, where did that decimal come from? It's the fact that, for instance, if, say, angle B right here was, say, 26 degrees, that a right triangle, and that ends up being the key operative right there, but if a right triangle with a 26-degree measurement, if I know those two angles, then by the AA theorem, something we talked about in Chapter 8, the AA theorem, I would have all right triangles with a 26-degree corner like that. All of them would be similar. And what does that mean? If all those triangles are similar, that means they are all scale models of each other, which means fundamentally you have some common scale factor, and that value is determined by these trig ratios. Okay, so it kind of does the work for us, thankfully, in a calculator. So just to kind of briefly show you again on my scientific calculator, you'll all recognize these from your own, but you've seen these sin, cos, tans. We talked about tan in Section 4 being tangent. Sin, cos, these are sine and cosine ratios. And the nice thing about these guys is that if I want to, say, take the sine of 26 degrees, I hit this sine button, it basically works out that scale model factor without having to go through all of that corresponding side nonsense that we had to in Chapter 8. So it's like shortcut buttons, basically. And it has to do, again, with one of the most important critical shapes in the geometric world, the right triangle. And so these sine, cosine, tangents are where those things come from. And again, in Section 4, we talked about the tangent being the following ratio: some side opposite a given angle, and then the adjacent or next to side angle. And what we learned in Section 4 is that it really depends on what angle I'm taking the tangent of. That determines what these values will be. So, for instance, I can take the tangent of angle B, or I could take the tangent of angle A. In either case, that kind of messes with what's the opposite side and what's the adjacent side. If I took the tangent of angle A, the side opposite would be this guy down here, and then the adjacent side would be this one right here. And it's worth pointing that out because when it comes to sine and cosine, you'll notice some of those same terms: opposite, adjacent. And now we have this new one. I say new, they've always been there, but the H in the Sohcahtoa, the H's, will refer to hypotenuse. And the reason we didn't have to worry about that with tangent is because there is no hypotenuse relationship there. It's not like it didn't exist. It's just that each of these three ratios exists because now it allows me to pick either of these two angles, and then depending on what information I have, depending on what side lengths I know and what side lengths I don't, I can solve for that relationship with any of these three. And the first one we talked about was tangent. Today we're going to talk about sine and cosine. So for OH, the SO, okay, again, commit this to memory, because when it comes to any trig ratios, this, much like PEMDAS with order of operations, this becomes the mantra, okay? So you'll hear me say it several times over, commit it to memory, write it down places so you don't have to forget it. But Sohcahtoa is going to tell us those relationships because it can get a little confusing with the different combinations. Toa was section 4's tangent, tangent being opposite over adjacent, Toa. Sine is going to be opposite over hypotenuse. And again, it depends on which angle I'm taking the sine of. So for instance, the sine of angle A would again be opposite. So this side length right here, but then it's over the hypotenuse. And the hypotenuse gets its own name because it is basically the significant side of any right triangle. It's always the longest of the three sides, the side that is opposite the 90-degree angle measurement. But for sine of angle A, it would be this length down here over the hypotenuse length. Whereas if I took the sine of angle B, now the opposite side would be this one, again, still over the same hypotenuse length. So just be careful. And it can help to kind of trace it out on your work and stuff. And then for cosine, the ca portion, A over H, cosine is adjacent over hypotenuse. So again, adjacent, if you need to write down your margin, adjacent literally translates as next to or sharing a border with. So for instance, if I were talking about angle A, the adjacent side would be this side that shares one of the corners or makes up part of that angle A. Okay, so this would be the adjacent side to angle A. This would be the opposite side to angle A. Whereas if I was talking about angle B, then the adjacent side here would be this one, the one right next to it. And then the opposite side would be that one. So it's really kind of location dependent. Okay, but Sohcahtoa, again, this is the main punchline. If you can handle this, you'll be able to handle this. And it's also worth pointing out that, again, this tends to be a confusing point for a lot of students that they forget this sort of thing. Like when I take the sine of something, when I take the cosine of something, tangent of something, that something is an angle measurement. It's a degree. Okay, so for instance, if this was 26 degrees, I could take the sine of 26 degrees and that would spit out something in a calculator, that ungodly decimal we saw earlier. Or if I took the cosine of that same 26 degrees or the tangent of that 26 degrees, I could take any one of these three trig ratios of that degree measurement. But each of those results is going to tell me how the fraction breaks down. And you can see that with each of these fractions, it's just relating two of the possible three sides in that triangle. All right, let me scroll down a little bit. Now, this is going to look really busy and maybe even intimidating. For the record, I just did the same thing in section 4. It's really just showing the long written out version of what the trig ratio does. So it can come in handy if you're trying to understand, like, wait, where did that come from? Okay. So for sine, again, it's just opposite over hypotenuse. So sine opposite over hypotenuse. Cosine is ca, or cosine adjacent over hypotenuse. All right, and then I show you like where that would be located in this triangle up here and stuff like that. Not all triangles will be labeled like this guy is. So sometimes the segment lengths would be a little bit confusing, or even if it's just labeled differently, it can be confusing. But we'll learn, particularly in the next section, how to just identify pieces rather than trying to identify actual names of segments and stuff. But this is just kind of the long-winded version or the more formalized version of what I just talked about. It's still going to break down to this. Sohcahtoa. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If you can handle that, you've pretty much got trig down. All right, well, we're going to do two examples. And this first one is going to be pretty typical of any trig type problem. All right, so what we're going to see is you're going to be given a diagram. It will be a right triangle, and you're going to be given some information in that triangle. And based on that information given, it's going to be pretty limited. And I'll describe that when I jump to the whiteboard. But based on what we're going to see, we're going to have to pick and choose which trig identity we're going to apply. All right, so as you can see in this diagram, I have a couple of unknown side lengths. I know the hypotenuse length in this diagram, and I'm given one of the other acute angles. Okay, so in this problem, we're being asked to solve for the missing variables, x and y, and then round any decimals to the nearest tenth. Okay, so again, pretty typical example of what you're going to see in this section assignment, in any trig assignment for that matter, and any trig problem you'll be tested on. So let's see this on the whiteboard and let me explain why trig is going to be used here and no other strategy will be as helpful. All right, so again, what's typical of a trig type of problem? You have a right triangle. as shown here. And then we're given a couple pieces of information. So before I write down the unknowns, let me start with the pieces that we explicitly know. Namely, we know that the hypotenuse here is 14 units long. Hypotenuse, again, being the side that's opposite the 90 degrees. Of these three side lengths, whatever these two side lengths turn out to be, they need to be smaller than this 14. That'll be a nice little sanity check for us as we get through our answers. Okay, so this should be the longest, the largest of the three numbers. And then we are given this angle here. We're told that this one's 26 degrees. So for the record, based on just that information, I can go through the process of solving this missing angle. I'm not asked for it, but I could because of the triangle sum theorem, because all three of these angles have to add to 180 degrees. I already know this one's 90. I know this one's 26. I can use that to figure out what's left over for this angle here. Again, not necessary. It's not asking me, but I could find that. And just to relate how, again, this connects back to like why we have trig ratios and stuff, the fact that this angle here is 26 degrees means that any variation of a right triangle that has the same kind of combinations of measurements. So for instance, if I had another right triangle who had, again, a 26 degree angle measurement, even though this one's much smaller in scale, it would be similar to this one. Okay, so if this one was 14 units long, this one would very obviously be much smaller, but there would be some scale factor, some multiplier that would take whatever side length value we had here and translate it over here. And why can I compare these two triangles? Because in chapter 8, we learned about something called the AA theorem, that if I have two angles congruent to two angles in another triangle, they are forced to be scale models of each other. And the ratio, the scale factor K that turns this guy into this guy, or vice versa, is what the sine, cosine, and tangent ultimately represent. So for instance, if I wanted to find the sine of angle 26 right here, which would compare this opposite side to its hypotenuse length, and we're going to do that for our first solution to this side length, whatever this fraction reduced down to, this side length over this side length, whatever that reduced down to, would have to be the same ratio as this much shorter one to this shorter one. Okay, the sine of 26 degrees will always be the same value. That's why it doesn't bother with like, all right, well, what's side lengths here? So if I put in 26 degrees and then take the sine of it, this gross looking decimal, that 0.438, basically tells me the scale factor that compares this side length to this side length, regardless of the actual size of the triangle, whether it's microscopically small or much larger, like a global scale or something like that. Okay, but again, that's just what a trig ratio is. All right, so anyway, back to our original diagram right here, this regular triangle. Then we're told that my unknowns are x and y. And I'm going to have to solve for these side lengths. Now, just to relate this back to section 1, section 1 in this chapter, we dealt with the Pythagorean theorem. And technically, the Pythagorean theorem here still applies. Why? Because I'm dealing with a right triangle. But the problem here is I can't use Pythagorean theorem yet. And I say yet because maybe I can at some point, but fundamentally, if I'm going to use Pythagorean theorem, I need to know at least two of the given side lengths. And in this case, just as it's given, the only side I know is the hypotenuse. Because if I try, say, solving for x using Pythagorean theorem, I'd have x squared plus y squared equals 14 squared. Problem there being I have two unknowns. So I actually can't get one by itself. Right? So fundamentally, if I'm going to be using Pythagorean theorem, I would have to solve for one of these two guys before I could use it. And thankfully, that's where trigonometry enters. And this is, again, where we're going to want to know this mnemonic, Sohcahtoa. So as soon as I know I'm using trig, and how do I know I need to use trig? Because I have a right triangle where I don't have enough information to use Pythagorean theorem. If I know some information about angles, I can compare any two of the sides in order to use trigonometry. Okay, so I have options here. Technically, I have three different trig ratios I could apply here: sine, cosine, or tangent. Well, let's first attempt tangent, right? I know this guy's 26 degrees. So if I were to take the tangent of this angle 26 degrees right here, that would give me some weird decimal on my calculator. But again, it's going to compare two sides, opposite and adjacent. So what's opposite 26 degrees? Unknown, x. What's adjacent to 26 degrees? Unknown again, y. So again, much like with the Pythagorean theorem, I run into a problem. I have too many variables. So tangent isn't necessarily going to be helpful in this case. And it makes sense that it'd be one of these two guys I'd be using, since that's the very name of this section, sine and cosine. So I just had to be careful. I actually could use either one. It's just going to be helpful in figuring out one of these two guys. Let's start first with x. Let's say I want to start with x first because it's alphabetical and I'm OCD that way. So if I want to solve for this x value, I want to compare it so that I don't have two unknowns in the same equation. I just want to have a single unknown, and that way I can get that unknown by itself and solve for it. So in this case, if I'm comparing this 26 degrees, x is opposite the 26 degrees. And then the other one that I actually know here is the hypotenuse, this 14. So I have opposite and hypotenuse, OH. I'm going to be using sine. So if I take the sine of that 26 degrees, which again, for the record, this is an actual number. It's going to be a gross decimal. We've seen it a couple times already, but it is an actual number. It represents a ratio. What ratio? Opposite over hypotenuse. And so this ratio, opposite over hypotenuse, I'm just looking compared to where that 26 degrees is located. So it's opposite 26 degrees. This is my unknown, the piece I'm solving for, x. And then the hypotenuse here is this leg right here, or not leg, the hypotenuse itself is the longest side, being this 14 unit side. So whatever the sine of 26 degrees is, and no matter the size and no matter what lengths I have here, sine of 26 is actually always the same number. It was that crazy 0.438 number that we saw in the calculator a couple times now. But that sine of 26 degrees has to be the reduced version or whatever this division problem would result in. So how do I solve for my variable x? If you can set this up, this is the hard part of the problem. Okay, if you can set up the correct trig ratio, okay, where I have some sine, cosine, or tangent of some degree measurement, and then I have the correct or OA, okay, in this case, sine O. So as long as I have this correct, I've done the hard part. Now I have to do a little bit of inverse operations to get the x by itself. So in order to get this x by itself, I need to get this 14 away. The 14 is being divided, so I'm going to move it by multiplication. So I would take 14 times that sine of 26. Again, sine of 26 is an actual number. And that's going to officially solve for my variable x. Great. So I've actually, before I've even pulled out numbers and stuff, I have x solved for. So I just have to do the calculator work. Again, this is the hard part to just set up at the beginning. This part right here is now just algebraically moving stuff around, so I've gotten the variable by itself. And now at this point, I just have to do the calculator work. So let's see it. All right, sine of 26 degrees. Again, there's that sin button. I get this crazy decimal. Again, just breaking down the ratio of any opposite of 26 degrees over all hypotenuse of a 26 degree angle. All right, well, there's sine of 26. I just have to remember to multiply it by this 14. And there we go. Now my answer said to round to the nearest tenth, so I would just round this decimal to the nearest tenth, which would be 6.1 is approximately x. Great. All right, quick sanity check. As I said at the beginning of the problem, the hypotenuse should be the longest side. Fundamentally, this number should be bigger than this number. It is. Okay, we're good so far. Next is this. Now that I know that this side here is 6.1, now I actually can use the Pythagorean theorem. Because now I know that this one's 6.1, so I could take 6.1 squared, add it to this unknown y squared, set it equal to 14 squared. So algebraically, I would say, all right, 14 squared minus this 6.1 squared, take the square root of it, I should be able to find y. So for the record, now that I have two sides of this right triangle, I could use Pythagorean theorem at this point. And that's totally acceptable. For the sake of this section's notes, I'll go ahead and do another trig identity, though, just so we can kind of get the practice. All right. So again, Pythagorean theorem can be used at this point now that I have one of the other two sides. But let's go ahead and apply a different trig identity. Now let's solve for y. And I could have done this first, for the record. All right, so again, I want to compare it to this 26 degrees. Right? This y is the adjacent side. It's the side that shares one of the wedge sides of this angle, right? So y would be adjacent. There's an a, okay? And I still know this guy, the hypotenuse, 14. So I have an A and H, adjacent hypotenuse, AH, meaning I'm going to be using this combination, cosine. So I could set myself up with this one. The cosine of 26 degrees has to equal adjacent over hypotenuse. And now I just have to fill in the gaps. So adjacent to the 26 degrees, this is my unknown. This equation is actually going to look very familiar to the last one. And then hypotenuse here is still 14 units. So this looks almost exactly like our setup for the sine. It's just that I have a different trig ratio here. And that's going to end up making a difference because the cosine of 26 degrees is a very different ungodly decimal than the sine of 26 degrees is. So again, this is the hard part of the problem, being able to set myself up with the trig identity. At this point, now I again need to get the variable by itself, meaning I need to move this denominator out of the way. So in this case, I would multiply both sides by 14. Again, looking very similar to the last one. I'm going to have 14 times now the cosine of 26 degrees. And this is going to equal my unknown variable, in this case, y. All right, now at this point, this is just calculator work. Right? Cosine of 26 degrees is an actual weird number. Let's go ahead and see that. So the cosine button is the cos, C-O-S. So if I take that, you'll notice a different ungodly decimal here. Again, this decimal represents the relationship of, for 26-degree angle right triangles, the relationship of the adjacent side to the 26 degrees over its hypotenuse. That's what that ratio will always break down to, whatever the values end up here being. So in this case, the fact that I know one of them, now I'd multiply it by 14 to figure out what has to be locked in on the numerator here, which in this case is about 12.6. And for the record, this value would have been discovered using Pythagorean Theorem as well. If you were to do 14 squared for that hypotenuse and subtract out that 6.1 squared leg, and then take the square root of it, you'd find that you'd get about 12.6. So whether you solve for one and then use Pythagorean Theorem or use two different trig ratios to solve for plus sides, you should get the same result. Okay, but that, again, is kind of a typical illustration of how you'll see trig problems presented. You'll be given a right triangle. You'll typically be given one of the side lengths and an angle measurement and asked to find the missing piece, but we'll deal with some other variations of that in tomorrow's section, or sorry, section 6 as well. All right, but let's move on. We have one more example. This one's a little more abstract, and you'll see what I mean when I come to it. So again, commit to memory, Sohcahtoa, because I just erased it. All right, last problem for section 5, down here at the bottom. Again, a little more abstract. So before we get too deep into it, let me first cover this up because this is something I've actually added as a hint. So let me come back to that. Here's what we'd actually be given in a word problem form. Given that the cosine of theta, now let me take a brief step to the side here, off to the margin right here, theta, this symbol looks like an O with a line through it. This is a Greek letter. Greek letter theta is just part of their alphabet. And the reason why these Greek letters exist, in math and science, you get so many variables, so many different variations and like unknowns and stuff that we have to dip into other language alphabets in order to fill them out. But in math and science, typically speaking, unknown angle measurements are usually given the designation of theta. Okay, it's no different than X, Y, A, B, J, all, it doesn't matter. It's an unknown, right? The fact that it's a Greek letter is just that mathematicians, scientists typically use theta as an unknown angle measurement for whatever reason. Okay, so in this case, it's just saying, given that cosine of some angle is 3/5, find the sine of that same angle and the tangent of that same angle. So again, we're given one of the trig ratios broken down into its fraction ratio form. And then based on that result, we need to find the other two trig ratios for that same angle. Okay, and I give you a hint here that the sine, cosine, tangent can only be used on right triangles. The key operative there being right triangles, and I'll come back to that in a second. So we're going to start with the fact that we have a right triangle. And anytime I take the sine, cosine, or tangent of an angle, I'm not doing it for the actual right angle, 90-degree angle measurement in that triangle. I'm doing it for one of the other two angles. So when I create my little diagram here of just some generic right triangle, and I plug in my unknown theta, and it really doesn't matter which place it goes in, but I'm going to designate it a position for a simple purpose. Now that I've designated it a position, that unknown angle, this mysterious angle that it's given me, the reason why this is a valuable hint right here, that they tell me that the cosine of whatever angle measurement this ends up turning out to be, whatever many degrees, big or small, since it equals this ratio, again, keep in mind Sohcahtoa, cosine, ka. That's going to be adjacent over hypotenuse. Why is that valuable information? Because if I designate my unknown angle here, the adjacent side has to be 3 units long, or at least the ratio has to be 3 units long. So what side is adjacent to or next to this unknown angle? This one. And if this guy's 3 units, I know obviously that's not how it looks on this diagram, but that's okay. But if this guy's 3 units, based on what they told me, the denominator here, again for ka, the denominator here is h, hypotenuse, meaning that the hypotenuse of this triangle is 5 units long. So now I know this one's 3, this one's 5. Based on that information, I could use Pythagorean theorem to find my missing piece. And once I know all 3 side lengths, then I just have to use Sohcahtoa to figure out, like, all right, well, what's opposite and then over hypotenuse of that angle? What's opposite and then over adjacent of that angle? Okay, so let's jump to whiteboard and see that worked out. So again, we're told that the cosine of some unknown angle is the following ratio, 3/5. And because it's cosine, I know that it has to be adjacent over hypotenuse because of ka, Sohcahtoa. All right, so that when I draw some generic right triangle, and it really doesn't matter what it looks like as long as it's a right triangle. And when I take the sine, cosine, or tangent of any angle, it's always going to be of one of the other 2 acute angles. So why not? I'll just call this guy the one I'm trying to solve for. All right, that's theta. So now I've actually know 2 of the 3 sides of this triangle. The side adjacent to this designation is 3. So this guy down here would be 3 units long. Hypotenuse is this guy, so that has to be 5. I now know 2 of my 3 sides of this right triangle. And using our section 1 strategy of Pythagorean theorem, if I have 3 squared plus my unknown length squared, we'll call that x, equal to my hypotenuse squared, I end up with this result. Well, these can be solved for. That's 9, and then I still have x squared, and this is 25. Now, if I subtract that 9 to the other side, I get x squared equals 16. These are just, again, this is the strategy we did in section 1. Now, taking the square root of both sides, I actually get a nice, friendly whole number. What did that actually mean? So just to reference another thing in section 1, the fact that I got 3 nice whole numbers, this is what we would call a Pythagorean triple. So that 4 unit would be right here. I'll go ahead and write that in. So now I know all 3 sides of my right triangle in their respective positions. Again, if I designate this as my unknown angle theta. Okay, well, that's not entirely what it was asking me for, not directly at least, but now let's get to what the question was actually asking for, which is, all right, now find the sine of that same angle, that same unknown theta, which is going to be some ratio. Again, for sine, that'd be so it'd be opposite over hypotenuse based on that position. And then I'm also asked for the tangent of that same angle. In this case, it's going to be the opposite over adjacent to that relative position. Well, actually, now that I know all 3 sides relative to that position, I can just plug in the stuff as I see it. Sine, Sohcahtoa, is going to be opposite over hypotenuse. What side is opposite the theta? The one I just solved for, the 4. That has to be in the numerator. Denominator has to be hypotenuse. Well, the hypotenuse is the same exact one from the ka for the cosine, so that one's going to be 5. Just double check to make sure you have a reduced fraction. This one's reduced. So what's the sine of theta? 4/5. Tangent of theta, or toa, is going to be opposite over adjacent. What's opposite this theta again? That same 4 that we used for the opposite in sine. And then the for adjacent is going to be this guy right here, the 3, the same adjacent that came from my cosine. And so double check that's reduced. This one is. What's the tangent of theta? 4/3. So again, this one was a little abstract because I had to kind of build my own diagram. This one was not given to me. I had to kind of imagine it. But again, they actually told me quite a bit of information just with this piece. I just had to, again, go back to Sohcahtoa to understand what each of these pieces represented. Using that, we were able to find our third side of the right triangle. Happened to be a Pythagorean triple, won't always happen. But based on that result, I can actually build both of the other trig ratios because now I have all three sides. It's all illuminated. Okay, but that will conclude our section 5 notes. I'll go ahead and stop recording right there.